Suppose f and g are differentiable functions. Then for a point on the parametric curve x equals f of t, y equals g of t, where y is also a differentiable function of x, we have dy dx equals dy dt over dx dt, provided that dx dt is not equal to 0. So this is pretty easy to prove by the chain rule, because if y is a differentiable function of x, then we can write dy dt as the product of dy dx and dx dt. You can imagine the dx is canceling out over here and just leaving you with dy dt. So we can solve for dy dx by dividing both sides by dx dt, and we get dy dx is equal to dy dt over dx dt. Similarly, we can find the second derivative using this method, because the second derivative is equal to the derivative of dy dx. So you can pretend that this is like a new y. So that's like saying that the derivative of this new y with respect to x is the derivative of y with respect to t over dx dt, which is the same as we were doing before. So we just have to be a little bit careful. If we want dy dx, we have to take dy dt over dx dt. If we want the second derivative, then we have to differentiate the previous derivative we got and divide by our original dx dt again. So let's do some examples of this. A curve C is defined by the parametric equations x equals t squared, y equals t cubed minus 3t. Let's show that C has two tangents at the point 3, 0 and find their equations. So we want to see the t value where y is 0, so we could see the point at which these tangents occur. So that means that we want to know when y, which is equal to t cubed minus 3t, which we can factor out the t to get t times t squared minus 3 is equal to 0. And that happens when this t is 0, or when this factor is 0. So that means we have t equals 0, or t equals plus or minus rad 3. So we can plug in t to evaluate x and to evaluate y, and we'll get that our point is at 3, 0. 3, 0 is at the value of t for plus or minus root 3. Notice it gets squared over here, so the minus or plus still gives the same x value of 3, and over here it's 0 either way. So now that we know what our point is, let's find what our derivative is. So we can't just use dy dt, because the slope of our tangent line is dy dx. So we calculate dy dx by taking the derivative of y with respect to t and dividing it by the derivative of x with respect to t. So if we look at dy dt, well, y is equal to t cubed minus 3t. So taking the derivative with respect to t, we get 3t squared minus 3 by the power rule, and then dx dt is just 2t. So we can factor out the 3 over 2 and get, when we divide t squared by t, we get t minus 1 over t. So let's look for at t equals plus or minus root 3. We'll have dy dx. If we plug in t equals plus or minus root 3 will be equal to plus or minus 6 divided by 2 times the square root of 3, which is coincidentally also plus or minus root 3. So that means that we get equations for our tangent lines. Well, it's y equals, y minus y1 equals m times x minus x1. So y minus 0 is just y. Our slope m is square root of 3. And x minus our point at 3. We also have our slope negative 3, same point. So those are our two tangent lines at the point 3, 0. Let's now find the points on C where the tangent is horizontal or vertical. So the tangent will be horizontal when dy dx is equal to 0. So if we have dy dx equal to 0, then we must have the numerator dy dt is equal to 0, while our denominator dx dt is not 0, so that we don't have any undefined business. So that means that we want dy dt, which is equal to 3t squared minus 3, which we could factor out 3 to get t squared minus 1 to be equal to 0. So that happens when t is equal to plus or minus 1. So this means that we get a horizontal tangent, ht, at the points where t is plus or minus 1. So if I plug in plus or minus 1 for t for x, then I get 1 when I square it. So that'll be at 1 for x, and then plus or minus 1 gives me plus or minus 2 for y. So I get 1 minus 2 and 1, 2 for my points where I have a horizontal tangent. To figure out where we have a vertical tangent, let's look at where dx dt is equal to 0. So where dx dt is equal to 0 is where dy dx will be undefined because dx dt is in the denominator. So instead of looking at that, I could say dx dt is equal to 2t. I'll look where that is equal to 0. So that means that t must be 0. So I have a vertical tangent at 0, 0. Notice that dy dt is not 0 at 0, only dx dt is. Let's now determine where the curve is concave upward or downward. So we need to look at our second derivative then. So this is equal to the derivative of dy dx divided by the dx dt that we have. So if we take our dy dx, which we calculated was 3 over 2 times t minus 1 over t, then the derivative is just 3 over 2 times 1 plus 1 over t squared. And dx dt is still 2t. So simplifying, we get 3 times t squared plus 1 over 4t cubed. So t squared is always positive, we don't have to worry about that. T cubed will just carry on whatever sign we have. So that means this thing is positive when t is positive and it's negative when t is negative. So our curve is concave upward when t is positive, and it's concave downward when t is negative. Let's now sketch our curve. So using all of this information, we have, well, let's get some axes first. So we have a point 3, 0. And at this point, we have 2 tangents. So if there's 2 tangents over here, we must cross, the curve must self-intersect over here. So it should look something like this. So this is one of those tangents. We'll do the tangents in another color, actually. So this could be the tangent y equals cube root of 3 times x minus 3. And then here's my other tangent. y equals minus root 3 times x minus 3. Notice also that we have horizontal tangents at 1 minus 2 and at 1, 2. So let's say it's like something around over here. So this is at t equals minus 1, and it's the point 1, 2. And then over here is at t equals 1, and that's the point 1 minus 2. Since our tangents over there are horizontal, we know we have a maximum minimum over there. We also know about the concavity. We know that this thing is concave up when t is positive and concave down when t is negative. So it should make sense it's concave down over here like this. Something like that. And it's concave up over here. So very roughly the curve looks something like that, where the t values are increasing like this. Let's find the tangent to the cycloid. X equals r times theta minus sine theta, y equals r times 1 minus cosine theta at the point where theta is pi over 3. So we should find dy dx. And that's, in this case, dy d theta, because we're using theta instead of t for our parameter, over dx d theta. So that's r sine theta. When we take the derivative of this guy with respect to theta, because this is a constant, so it's just gone, and the derivative of minus cosine times r is just r sine. And we divide by r times 1 minus cosine theta. Because that's this derivative, we get a 1 from theta because it's not constant. So this simplifies to sine theta over 1 minus cosine theta. So we need to look at theta equals pi over 3. So when theta is equal to pi over 3, that implies that x is equal to r times pi over 3 minus the sine of pi over 3, which is equal to r times pi over 3 minus rad 3 over 2. And let's get our y coordinate also. We get r times 1 minus cosine of pi over 3, which is r over 2. Our dy dx, as we've calculated, will be the sine of pi over 3 over 1 minus the cosine of pi over 3. So that's just rad 3 over 2 over 1 minus a half, which is rad 3. So plugging this in, we get y minus our y value, which is r over 2, equals our slope rad 3 times x minus our x value, which is r pi over 3 plus r rad 3 over 2 if you distribute. So this is the same exact thing as rad 3 times x minus y equals r times pi over rad 3 minus 2, if you like standard form better. So what this looks like is something like this. We're gonna try drawing at least a little bit of our cycloid. Remember, it's this ball that rolls around and creates these hill-like things over and over and over again as the ball rolls on forever. So it's something like this. Good enough. So here's our point where theta is equal to pi over 3, and here's our tangent. So at what points is the tangent line horizontal? When is it vertical? Well, we have to figure out when dy dx will be 0 and where dy dx will be undefined. So let's look for dy dx equaling 0 first. Well, dy dx is sine theta over 1 minus cosine. So that's 0 when sine of theta is equal to 0 and cosine of theta is not 0. Sorry, 1 minus cosine theta is not 0. Well, sine of theta is 0 at all of the odd multiples of pi, right? It's, 0, then pi, and then it'll be 0 again, and so on. So if we were to let, we can't consider this point over here at 2 pi, because then 1 minus cosine would be equal to 0 because cosine would be 1 over there. So we can only consider these values over here, all the multiples of pi. So we get that theta is equal to all of the odd multiples of pi. We can write that as 2n minus 1, because 2n minus 1 is an arbitrary odd number as long as n is an integer. So we write n in z. So this means that we have horizontal tangents at all of our odd multiples of pi, 2n minus 1 times pi times r, 2r, because we plug in theta for our x value and y value. So we have horizontal tangents at all of these x values of odd multiples of pi times r. So that's over here. Each of these is where we'll have a horizontal tangent. Actually, I won't do that one. I'll do this one. So we have horizontal tangents over here like this. And the first one's at pi r. That's our first 1 pi is, odd multiple of pi, and the height is 2r for every single one. So this one's at 3 pi r, 2r, and this one's at 5 pi r, 2r, and this one will be at minus pi r, 2r. Let's see where we have vertical tangents now. So we need to look for dx d theta, our denominator, to be 0, because that's when this thing will be undefined. So that's when theta is equal to 2n pi. So we should check theta equals 2n pi to see if we have a vertical tangent here. Notice dy d theta is also 0 here. So we have, let's do a limit. How about we check as theta goes to 2n pi from the right. So we're taking the limit of dy dx. We want to see that this limit is infinity, as if it is, then we have a vertical tangent there. So I keep forgetting my n. And I get sine over 1 minus cosine. But I can do L'Hopital's rule, take the derivative of top and bottom because this thing is indeterminate. So I do that, and I get that the derivative of sine is cosine, and the derivative of 1 minus cosine is sine. So then, as theta goes to 2n pi, cosine goes to an even multiple of pi, so cosine just goes to 1. And sine, on the other hand, goes to 0. So we have 1 over a very, very small number. It gets smaller and smaller. That means that dividing by a small number makes this value bigger and bigger and bigger. So this thing does go to infinity. So that means that we have a vertical tangent at all of the x equals 2n pi r x values you can get by just plugging in 2n pi for theta. You could also do the same limit for dy dx for theta approaching 2n pi from the left. You would get minus infinity. So this means that over here at 2 pi r and over here at 4 pi r and so on at 6 pi r, negative 2 pi r, etc., we have vertical tangents, which makes sense. Let's take a look at it. Looks like we have vertical tangents over there just from our picture. If a curve is traced out once by the parametric equations x equals f of t and y equals g of t, where t ranges from alpha to beta, then the area under the curve is given by the integral of g times f prime. So it doesn't matter if we go from alpha to beta or beta to alpha, we get the same area. We do this using the substitution rule, or u substitution, except that we don't actually have to throw in u because, well, we're doing everything in terms of t, so we're going to convert from dx to dt. We know that the area under the curve y equals f of x is the integral of f of x dx, so that means that if we go from a to b of this integral, we already know that's the area. So we just need a way to evaluate it. Remember that we don't necessarily have an explicit formula for y as a function of x. Instead, for each of these problems, we're given y in terms of some parameter t. So we need to convert this integral as some function of t. So we do that using substitution. We know that y is g of t, so we replace y with g of t. We replace our limits a and b with whatever corresponding limits alpha and beta correspond to those x values for t values. So now we just have to convert dx to some dt thing. So we have x equals f of t, right? So that means that dx is equal to f prime of t dt. So we just replace the dx with f prime of t dt, and that's it. So let's do an example of this and find the area under one arch of the cycloid. So it looks like theta goes from 0 to 2 pi if we want to just get one arch. So we have a restriction on theta from 0 to 2 pi, so that's probably what we'll have to integrate. And our y is equal to r times 1 minus cosine theta. So we'll substitute that into our integral for y dx. And our dx, let's take a look at this guy. If we take the derivative, we get r times 1 minus cosine theta d theta. So I think we have enough we can plug into our integral now. The area is the integral from 0 to 2 pi r, because we're still with respect to x. And we convert those limits. At 0, t is 0, or in this case, theta is 0. And at 2 pi r, theta is 2 pi. So y becomes r times 1 minus cosine theta. And dx becomes r times 1 minus cosine theta d theta. So that's pretty cool. We can pull out r squared. And we have the integral from 0 to 2 pi of 1 minus cosine squared. And we can rewrite that using FOIL. So we get 1 minus 2 cosine theta plus cosine squared. So we just have to integrate cosine squared. That's the only hard one. So we get the integral from 0 to 2 pi of 1 minus 2 cosine theta, and we'll replace the cosine squared with the half angle identity, half 1 plus cosine 2 theta. Because it's way easier to integrate that than it is cosine squared. So we get r squared times 3 over 2 theta when we do our antiderivative, minus 2 sine theta plus 1/4 sine 2 theta with a quick mental substitution for 2 theta. So we evaluate that from 0 to 2 pi and we get r squared times 3 over 2 times 2 pi, which is 3 pi r squared. So that's kind of cool. There's 3 circles in each cycloid, each arch of each cycloid. If a curve C is described by the parametric equations x equals f of t, y equals g of t, where t goes from alpha to beta, where f prime and g prime are continuous on the closed interval, and C is traversed exactly once as t increases from alpha to beta, then we get the length as the square root of the two derivatives dx, dy with respect to t squared. So this looks slightly different than what we did in section 8.1, but it's actually pretty much the same. If we use our formula from section 8.1, L equals the integral from a to b of the square root of 1 plus dy dx squared, right? 1 plus the derivative squared, we take the square root, and that gives us arc length. Then we can convert that using the substitution rule if we assume that y can be written as a function of x. So assuming that y is f of x, we get the integral from alpha to beta of the square root of 1 plus our derivative squared, but we already have our formula for a derivative. That's dy dt over dx dt, assuming that y can be written as a function of x. And then dx, as we saw before, was just x, the derivative of x with respect to t times dt. So what we can do is we can write this dx dt under a square root if we square it, and then distribute it, and then it'll cancel the dx dt over here in the denominator, and we just end up with this formula. However, the formula still works even if y cannot be written as a function of x. Notice that's not one of the hypotheses for this theorem. So if you want to prove that formula in that case, then you have to go back to the way that we proved it in section 8.1 for without parametric equations. It's pretty much the same method. You take your curve, you chop it up into little pieces, and you have to build a Riemann sum. I don't really feel like building a Riemann sum right now, so try it yourself if you're curious. Let's just do an example. So let's use the representation of the unit circle that we looked at last time, x equals cosine t, y equals sine t, and find its arc length. So we have dx dt equal to minus sine t, and we have dy dt equal to cosine t. So that means that our arc length L is equal to the integral from 0 to 2 pi of the square root of dx dt squared plus dy dt squared, and that integral is the integral from 0 to 2 pi of the square root of sine squared plus cosine squared. And so sine squared plus cosine squared is 1, so that's the square root of 1, which is just 1, so this is the integral from 0 to 2 pi of dt, which is just 1 times b minus a, so that's 1 times 2 pi minus 0, which is 2 pi. So how about we use the representation of the unit circle given by x equals sine 2t, y equals cosine 2t. Remember that this results in the exact same curve, but a slightly different parametric curve because this one's traversed twice. So we have dx dt equals 2 cosine 2t and dy dt equal to minus 2 sine 2t. So that means that our integral becomes the integral from 0 to 2 pi of the square root of dx dt squared plus dy dt squared. So that's the integral from 0 to 2 pi of the square root of 4 cosine squared 2t plus 4 sine squared 2t, which is the integral from 0 to 2 pi of 2 dt, which is 4 pi. So this does not equal our arc length. So if we wanted to actually find the arc length, we would have to take half of this integral, because notice that our theorem said that this thing had to be traversed exactly once. So these parametric equations in the second representation, as we've seen before, provide a curve that's traversed twice. So you have to be very careful with parametric equations. It's not always obvious how many times you've traversed your curve, but you have to be very careful if you want to actually find the arc length that you're not duplicating any sums. Let's find the length of one arch of the cycloid. So as we've seen, theta goes from 0 to 2 pi for one arch. So that means that we have to look at dx d theta, r times 1 minus cosine theta, and dy d theta, which is r sine theta, inside of an integral that just goes from 0 to 2 pi of the square root of each of these derivatives. So we get the integral from 0 to 2 pi of square root of r squared times 1 minus cosine theta squared plus r squared times sine squared. So we can write this as the integral from 0 to 2 pi of r squared, because we'll factor that out, times 1 minus 2 cosine theta plus cosine squared, by foiling that out, plus r sine squared. Okay, well that's sort of nice because we have cosine squared plus sine squared. Actually, how about I take out my r first? Remember, I have square root of r squared, so I'll just pull out an r. So I end up with the square root of 2 times 1 minus cosine theta. Because this is just gone. And I could just factor this out over here. Remember that cosine squared plus sine squared became 1, which made this a 2. So I want to try to get rid of this 1 minus cosine theta in my square root, so I can actually take the square root. So I need to get some trig function squared in here instead. So how about I use that half angle identity again? I know that half times 1 minus cosine theta is equal to, well, half times 1 minus cosine 2 theta is equal to sine squared. But I have theta instead of 2 theta. So I'll look at sine squared of theta over 2 if I want to go backwards. And because there's no half over here, I'll have to multiply by 2. So I end up with r times the integral from 0 to 2 pi of the square root. I'll keep my 2 on the outside. But now I have 2 times sine squared theta over 2. Replacing my 1 minus cosine theta using our half angle identity. So that's equal to r times the integral from 0 to 2 pi of 2 times the absolute value of sine of theta over 2. However, we're looking at this only from 0 to 2 pi. So sine is positive, so we can get rid of our absolute value very easily. It's just going to be sine of theta over 2. So we'll take our antiderivative now. We'll get 2r times minus 2 cosine theta over 2. Quick substitution in our head. And we evaluate that from 0 to 2 pi to get 2r times 2 plus 2, which is just 8r. So just like we did in section 8.2, you can find the area of a surface of revolution by using the formula 2 pi times your radius times the arc length. So we integrate this guy over here. You can prove it similarly to the way that you would prove it in section 8.2. So let's just use this and see if we can find the surface area of a sphere. So for a sphere, we have parametric equations. X equals r cosine t, y equals r sine t, where t goes from 0 to pi. Because what we're going to do is we're going to take not a circle and rotate it, because then if we took an entire circle and we rotated it around, then this part on the bottom would go to the top, and the part on the top would go to the bottom, so we'd traverse the sphere twice. Instead, what we're going to do is we're just going to take half of a circle, and we'll rotate that around the x-axis, and then that'll go and fill up and become a sphere as it rotates. So we'll restrict it to pi instead of 2 pi. So we end up with the surface area S equal to the integral from 0 to pi of 2 pi times our y value, which is r, times r sine t, times the square root of minus r sine t squared, because that's dx dt squared, plus r cosine t squared, because that's dy dt squared. So that becomes 2 pi times the integral from 0 to pi of r sine t times the square root of r squared times sine squared plus cosine squared. So that's wonderful, because that's just 1, so we just have the square root of r squared. So we have 2 pi times the integral from 0 to pi of r sine t times r, which is just 2 pi times the integral from, well, how would I pull up my r's, because they're constants, so 2 pi r squared times the integral from 0 to pi of sine t dt, which is just 2 pi r squared times the antiderivative of sine, which is minus cosine. And we'll evaluate that from 0 to pi. So minus 1 is 2 times 2 pi r squared is 4 pi r squared. So it looks like we can cover a sphere with 4 circles.